Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications, and is the second part of section 1.1, Systems of Linear Equations. We'll talk about how to solve a linear system by walking through an example problem. We'll learn what elementary row operations are, and then we'll look at an example to determine what values a parameter can be for a particular linear system to be consistent. Be sure to check out the link below for free guided notes that you can use while you watch this video. We'll start on page 6 of the guided notes. We're going to learn how to solve a linear system of equations by following a basic strategy. That strategy is going to be to replace one linear system with an equivalent system that's easier to solve. I've created steps that we can follow when we have 3 equations and 3 unknowns. We can then use steps very similar to this to solve a linear system that has more equations and more unknowns. As we go over these steps, I'm going to refer to the example that we're going to do below. The first step that we're going to do is to use the x1 term in equation 1 to eliminate the x1 term in equations 2 and 3. Our second step will be to use the x2 term in equation 2, right here, to eliminate the x2 term in equation 3. Notice that we're eliminating terms by working down and to the right. Our third step will be to use the x3 term in equation 3, right here, to eliminate the x3 term in equations 2 and 1. Here's equation 2, and here's equation 1. And then our last step will be to use the x2 term in equation 2. I'll mark that with a check since we already have it color-coded in yellow, to eliminate the x2 term in equation 1. Notice that for the third and fourth steps, we're eliminating terms by working up and to the left. These steps are very similar to the ones that we'll be using in Gauss-Jordan elimination. Things to keep in mind as we follow these steps are to rearrange the equations at the beginning, if it will help. You'll need to do that if there's no x1 in the first equation. And to divide an equation by a constant as we go along, if it will help. Before we start our example, I'm going to erase what we highlighted so that we can highlight again as we go along. We're going to solve this linear system algebraically, and we're also going to solve it using an augmented matrix. So before we begin, let's go ahead and let's set up our augmented matrix. The other thing we're going to do before we begin is I'm going to label the equations and label the rows. We'll call this first equation E1, this one E2, and this one E3. Likewise, we'll call the first row in our augmented matrix R1, the second one R2, and then the third one R3. We'll now walk through the steps that were listed above. Our first step is to use the x1 in equation 1 to eliminate the x1 in equations 2 and 3. To eliminate the x1 in equation 2, we just need to add equation 1 to it. We're going to notate that as equation 2 becomes equation 2 plus equation 1. Let's go ahead and write down equation 1 and then our new equation 2. So equation 1 stays the same. And then our new equation 2 is going to be x1 minus x1, which is 0, and then x2 minus 2x2, which gives us a minus x2, and then 2 plus 3 is 5, so we pick up a 5x3, and then we have 8 plus 1, which is 9, because we're just adding those two equations. To eliminate the 3x1 in equation 3, we need to multiply equation 1 by minus 3. We'll notate that as equation 3 goes to equation 3 minus 3 times equation 1. When we do that, we get 3x1 minus 3x1 is 0, and then we get minus 7x2 minus 3x2 gives us a minus 10x2, and then 4x3 minus 6x3 gives us a minus 2x3, and then 10 minus 24 gives us a minus 14. Let's now see how we would do that same process for our augmented matrix. We're going to use the 1 entry in row 1 to eliminate the negative 1 and 3 from rows 2 and 3. Our notation is going to be really similar. We're going to say that row 2 becomes row 2 plus row 1, and then row 3 becomes row 3 minus 3 times row 1. Once we get used to doing this process and get more familiar with our elimination algorithm, we won't be writing this type of notation down. Our augmented matrix now looks like this. 1, 1, 2, 8. And then we're going to add row 1 to row 2. So we get 0, minus 1, 5, 9. And then we'll multiply row 1 by minus 3 and add it to row 3. So we get 0, minus 10, minus 2, minus 14. Before we do step 3, where we're going to use the x2 term in equation 2 to eliminate the x2 term in equation 3, let's multiply equation 2 by negative 1 and multiply row 2 by negative 1. It will make it easier if we have a positive x2 to work with. We'll notate this as equation 2 goes to minus 1 times equation 2, and then row 2 goes to minus 1 times row 2. Here's what we get then. We're going to multiply the negative by all 3 terms. That's often a mistake students make, is to not carry that negative all the way through. And then our augmented matrix is going to look like this. We're only changing row 2. So we have a 1, 1, 2, and an 8, a 0, 1, minus 5, minus 9, and then our third row is the same. Now we can go on to our second step. We're going to use the x2 term in equation 2 to eliminate the x2 term in equation 3. Likewise, we'll use the 1 in row 2 to eliminate the minus 10 in row 3. We would say that E3 is going to become E3 plus 10 times E2. And then likewise, we'll say that row 3 becomes row 3 plus 10 times row 2. I'm going to copy what we just wrote onto our next page so that we can continue on. Our first and second equations are going to stay the same, and it's just the third one that's going to change. So we have x1 plus x2 plus 2x3 is 8. We have x2 minus 5x3 is minus 9. And then now we're multiplying equation 2 by 10, adding it to equation 3. We get a 0 for the x2. We end up with a minus 52x3. And then minus 9 times 10 is minus 90, minus 14 is minus 104. On the right-hand side, with our augmented matrix, we have 1, 1, 2, 8, 0, 1, minus 5, minus 9, and then 0, 0, minus 52, minus 104. I want to point out before we go on that before we started step 2, we also could have multiplied row 3 or equation 3, by a minus 1/2, and that would have made the number smaller. We're going to do one of those simplifications now, because before we use the x3 in equation 3 to eliminate the x3 in equations 2 and 1, we would like to have just a 1 multiplying x3. So we say that E3 is going to go to minus 1 divided by 52 times E3. Likewise, in our augmented matrix, we're going to have row 3 become minus 1 over 52 times row 3. I told my students in class yesterday that this is the only time that we're going to be working with the algebraic part, but I think it's worthwhile to do this so that you can really see why we're doing the row operations that we're doing. Our augmented matrix then looks like this. And we have a nice 1 to work with instead of a minus 52. Now we're ready to begin step 3. We're going to use the x3 in equation 3 to eliminate the x3 in equations 2 and 1. Likewise, we're going to use this 1 entry to eliminate the minus 5 and the 2 entries. To eliminate the x3 in equation 2, we'll say that equation 2 becomes equation 2 plus 5 times equation 3. Likewise, equation 1 is going to become equation 1 minus 2 times equation 3. For our augmented matrix, our row 2 is going to become row 2 plus 5 times row 3. And then our row 1 is going to become row 1 minus 2 times row 3. You might start seeing that it's actually easier to work with the augmented matrix and not have to write down all the x's. Since we're working from equation 3 up to equation 1, we're going to start writing our linear system with equation 3. So we're going to write x3 is equal to 2. Then we're going to multiply this equation times 5 and add it to the next one. So we're going to get an x2 and then a 0, and we're going to get 10 minus 9, which gives us a 1. And then our first equation is x1 plus x2. We have no x3, and then we have 2 times negative 2 from right here, adding it to 8, and we get 4. For our augmented matrix, it looks like this. It's a little awkward, but get used to writing the bottom row first. And then we multiply that row by 5, add it to the second row. So we get 0, 1, 0, 10 minus 9 is 1. And then we multiply the bottom row by negative 2 and add it. And we have 1, 1, 0, minus 4 plus 8 gives us a 4. And we're almost done. We just have one more step to do. We'll label this as our 4th step. So we'll use our x2 in equation 2 to eliminate our x2 in equation 1. Likewise, we'll use this entry in row 2 to eliminate this entry in row 1. Let's write that down. So E1 is going to become E1 minus E2. And then row 1 is going to become row 1 minus row 2. Hang with me, we're almost done. You can do this. We get x3 is 2. We have x2 is 1. And then we're multiplying this equation by minus 1, adding it to this equation. So our x2 goes away, and we end up with x1 is equal to 4 minus 1, which is 3. For our augmented matrix, we have 0, 0, 1, 2, 0, 1, 0, 1, and then we're multiplying the second row by negative 1, adding it to the first row, and we get 1, 0, 0, 3. Our solution can then be written as x1 is equal to 3, x2 is equal to 1, and x3 is equal to 2. Notice we're writing the x's in ascending order. Or we could just write our solution as a point, 3, 1, 2. I want to remind you down here at the bottom that linear algebra has some really great built-in checks, and you can take this solution, 3, 1, 2, plug it back into the original linear system, and check to make sure that you have the right answer. Let's just go ahead and let's do that. So right here, here, and here, we can plug in x1 is 3, x2 is 1, and x3 is 2, and make sure that we get the same number on the left as we do on the right. Let's now go to page 8 and talk about elementary row operations. Row operations are the algebraic operations that we've been using to reduce an augmented matrix to a more simple augmented matrix where we can easily find the solution. We just did this in the previous example. We started with the augmented matrix on the left, and we ended up with this augmented matrix on the right. So you can see that the augmented matrix on the right easily tells us that our solution is 3, 1, 2. These augmented matrices are what we would call equivalent, because they produce the same exact solution. There are 3 elementary row operations. The first one is called replacement, and that's when we replaced one row, and I just noticed that that's not spelled right. So let's make that change. You're going to replace one row by the sum of itself and a multiple of another row. This is exactly what we've just been doing. So for example, a row replacement might look like this. We could take row 2 and replace it with row 2 plus 3 times row 1. That's called row replacement. Our second elementary row operation is called interchange, and that's when we interchange 2 rows. We actually didn't do that in our previous example, but if we would have done it, we would have notated it like this. Row 2 gets switched, and we'll put an arrow on both ends, with row 3. Our third row operation is scaling, and that's when we multiply all entries in a row by a non-zero constant. You wouldn't want to multiply a row by 0 because you would then be eliminating that row or an equation, and you would lose some information about your linear system and change it. Scaling is going to look like this. We could say that row 2 gets scaled by a factor of 1/2. The last topic that we're going to learn about is consistent linear systems. In a previous video, we learned that there can be 3 solutions to a linear system of equations. No solution, exactly one solution, or infinitely many solutions. If we have no solution, our linear system is called inconsistent. And if we have exactly one solution or infinitely many solutions, our linear system is called consistent. Down at the bottom here, I've written down 3 linear systems of equations. By looking at the structure of these 3 systems, we're going to see if we can determine what type of solution they will have. Our first linear system has an equation 0 is equal to 15. This can't happen, so this is an example of a linear system that has no solution. Our second linear system has a solution for x3, and then we could plug this solution back into our second equation and get a solution for x2, and then we could substitute x3 back into the first equation and x2 back into the first equation and get a solution for x1. So this linear system is an example of a linear system that has one solution. Our third linear system has an equation for x1 and an equation for x2, but no equation for x3. x3 is what we call a parameter. And because of that, this linear system has infinitely many solutions. In class, I had a student ask a question and they said, could we solve this last linear system for x2 and x3 and then x1 would be our parameter? The answer is yes, absolutely. However, it's usually standard to solve an equation for the variables 1 all the way up through whatever you have and let the later variables, such as x3, be your parameters. It just makes it a little bit easier to have a solution for x1 and x2. In this last example, which has a constant h in it, we're asked for what values of h is the following system consistent. In other words, what values of h will this following system have a solution? We're going to solve this algebraically using the same steps that we did for our earlier example. We'll call this equation 1, and we'll call this one equation 2. We're going to use our x1 term in equation 1 to eliminate our x1 term in equation 2. So E2 is going to be replaced with E2 minus 2 times E1. This is going to give us x1 plus hx2 is equal to minus 2. That one stays the same. And then we're going to multiply equation 1 by minus 2 and add it to equation 2. We get 0. And then we have 4 minus 2h times x2 is equal to minus 2 times 2, which is 4, plus 1 gives us a 5. When we want to determine if a linear system has a solution, just like we're being asked here to find out if it is consistent, we don't have to solve it completely. We can tell from this equation what values of h will give us a solution. So what we're going to do is we're just going to go ahead and solve for x2 algebraically. So x2 is equal to 5, all divided by 4 minus 2h. In order to have a solution, our denominator cannot equal 0. So we're going to have to say that 4 minus 2h cannot be equal to 0, and that gives h cannot be equal to 2. So our answer is going to be that our linear system will be consistent for all values h not equal to 2. When we get more equations and more unknowns, we need to be able to do this type of analysis just using matrices. So we're going to come back up to the top and we're going to do the same thing with an augmented matrix. Let's go ahead and write down what we have. We have a 1, h minus 2, and then a 2, 4, and a 1. And we'll label our rows as row 1 and row 2. We're going to use this 1 to eliminate this 2. So we're going to take row 2 and replace it with row 2 minus 2 times row 1. This gives us 1h minus 2. That part didn't change. And then we get a 0. We multiply row 1 by minus 2. So we get 4 minus 2h. And then 1 plus 4 gives us 5. Let's now focus on this row. What we want to avoid is having 0 times an x1 plus 0 times an x2 is equal to 5, because that would be 0 is equal to 5, and that of course won't have a solution. So we're going to have to say that 4 minus 2h cannot be equal to 0, because if it was, this term would be 0, and that would not have a solution. So this again is the same. H is not equal to 2, and that gives us our same answer. In the next video in this series, I'll teach you all about row reduction and echelon forms.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.